All right, guys, Mr. Antonucci here, and in this section, we're talking about volume of a solid with known cross sections, and we want to find that volume. So previously, we had looked at the disk method and the washer method, which we were finding the volume of a solid using circular cross sections, but we're not limited to just circles. You can use this idea for any shape as long as you have the formula for the area of a cross section. Common ones include squares, rectangles, triangles, semicircles. So the idea here is very similar. You want to cut the solid into thin slices using planes perpendicular to an axis and then add the volumes of all the slices to obtain the total volume. And like we said, this relies on the fact that the area of each cross section is known and can be expressed as a function of the position of the slice. So if you look at these examples we have here on the screen, this first one, we have a square cross section perpendicular to the x-axis. And then in this one, we have a square cross section perpendicular to the y-axis. Actually, this one that's perpendicular to the x-axis is not a square, so we wouldn't want to slice it like that. But if we sliced it perpendicular to the y-axis, then we would have better luck there. So the same kind of idea is involved here, where we're going to add up each slice, the area of each slice, multiply by the thickness of each slice, let the number of slices approach infinity. So in general, what we're going to end up with is the formula volume equals the integral from a to b of a of x dx. Essentially, you're just going to integrate the area function for the slice to get the volume of the solid. So here is our first example. This one we're going to cut using squares. So the base of a solid is the region R bounded by the x-axis and square root x, and the line x equals 4. So you can see here we have a graph of the square root, the line x equals 4, and the x-axis, and that region R is right here. In this other picture, I've kind of rotated it a little bit so that you can get more of a bird's eye view of it. What we're going to do is we're going to put cross sections perpendicular to the x-axis. If you look at this graph, we would put the slice vertically here. On this one, we would put it perpendicular to the x-axis there. And they're going to be rectangles with height x and width square root x. If you could imagine, this is the height or excuse me, the width, and this is the height right here. Okay, so as you move along the square root function, you can imagine these squares hopping out like this. So you would get kind of a solid shape there. So the area function, if we get that first, is going to be the height times the width, x square root x, which is x to the 3/2. And then x is going to vary from 0 to 4. So the volume is going to be the integral from 0 to 4 of x to the 3/2 dx. So we would have x to the 5/2 times 2/5 evaluated from 0 to 4. If you plug in 4 to the 5/2 power is like square root 4, which is 2. 2 to the 5th power is 32. And then plugging in 0, you would get 0. And so this is going to be 64 over 5 cubic units. Let's go ahead and move on to another example. In this one, we're going to look at a situation where we use triangles. So a solid has a circular base of radius 3 units. We want to find the volume of the solid if every cross section that is perpendicular to the fixed diameter is an equilateral triangle. So we have a circular base of radius 3. We have the circle of radius 3 that forms the base. And what we would imagine is triangles that are stacked on top of the circle there. You could think of this as a representative triangle here, and that's going to be stacked on top of the circle. So as the triangles goes from left to right across the x-axis, it's going to get bigger and smaller dependent upon the diameter. If this circle has a radius of 3, its equation is going to be x squared plus y squared equals 9. Each cross section is of the solid is an equilateral triangle. So the side length is going to be 2y and the height h. And so the area is equal to the square root of 3y squared. Okay, now from our circle equation, we know that y squared is equal to 9 minus x squared. So we could substitute that in, and you get 3 times 9 minus x squared. That's going to be our volume, or excuse me, our area formula for this one. Now, the volume is equal to the integral from -3 to 3 of square root 3 times 9 minus x squared dx. So I'm just going to factor the root 3 out. The antiderivative of 9 is 9x minus the antiderivative of x squared is x cubed over 3. Then we would plug in -3 and 3 and subtract. And this would simplify all the way down to 36 square root of 3 square unit. All right, guys, well, that's it for this video. Hope that was helpful to you. Reach out if you have any questions.